In this video, we'll steer away from steels and focus on something more general, that's precipitation in alloys. We will start from an example not in alloys, but in water-based solution. Assume you have like water and salt, you keep adding salt into water, and at a certain point, it will reach saturation. And after that, you keep adding extra salt, and these salt crystals will precipitate out. The salt water is the primary phase, we call that the matrix, and the salt that cannot be dissolved in the water, that's called second phase or precipitates. Next, you heat the system up. As you increase the temperature, the solubility of salt in water will increase, and the remaining salt, these precipitates, they can be dissolved in the salt water at a high temperature. If you cool the system down very carefully, the excess amount of salt can actually stay in water solution to form the supersaturated solution. However, if you do some perturbation, for example, shake the beaker or put in some extra salt crystals, the excess amount of salt in the supersaturated solution will come out or precipitate out. The same idea can be translated to solid systems. In the metal systems, usually the starting material is either as cast or as hot extruded or as hot rolled, and you have some coarse second phases present in the microstructure. You heat up the system to the solution treatment temperature, hold it for a while. The second phases will dissolve back into the matrix. It's similar to the extra salt in water example. At high temperature, the solubility increases and the excess amount of second phases dissolve back into the matrix. At this condition, you will have a precipitate-free microstructure. As you quench the microstructure or cool down the microstructure very rapidly, you also retain this precipitate-free microstructure. The material is referred as the supersaturated solid solution. Next, you heat up the material slightly at a lower temperature compared to the solution treatment temperature, and you will have precipitates dispersed throughout the microstructure. The heating or aging here is analogous to the small perturbation you introduce to the supersaturated salt solution. The idea is to bring out the excess amount of solute in the form as precipitates. Before moving on, I'd like to make a few quick notes here. The first is the process you start by doing solution treatment, then aging to bring out precipitates is commonly used in a wide variety of alloys, including steels, aluminum alloys, magnesium alloys, nickel-based superalloys. So this method is universal. The second thing is when you think about alloy design, precipitate strengthening actually is the most effective strengthening method to make a metal stronger. So this approach has very broad engineering applications. The third point is you may wonder why at a lower heating temperature precipitates tend to come out. We call this aging, but at higher temperature we call solution treatment. That's when precipitates got dissolved back into the matrix. This has something to do with Gibbs free energy. We need to take enthalpy, entropy, and temperature into considerations. I will leave it to you to ponder more on this point. Next, we'll discuss the shape of precipitates. Intuitively, we may think precipitates should be all spheres. This is because as we have second phases in the matrix, we are creating interfaces. And interfaces, they can introduce interfacial energy, which is energetically unfavored. With the given volume of precipitates or the second phase, having a spherical shape introduces least amount of surface area, hence least amount of surface energy. That's why the intuitive way of thinking precipitates, we should have spherical ones. However, this is not what we usually observe in materials. If you look into literature, many of the experimental observations show precipitates are plates or disks. Here are some examples. In the first example on the left, the red plates are copper-rich precipitates in an aluminum-copper alloy, and the datasets are atom probe datasets. The top right example shows an TEM image overlaid with the orientation map. And you also see those precipitates. They appear to be rods, but actually they are indeed plates, and we are viewing those plates in the adjoint condition. In the bottom right example, these are precipitates in nickel, titanium, hafnium shape memory alloys. Each box represents one aging condition, and the data were reconstructed from TEM tomography. Regardless the aging condition, you can see all the precipitates, they show the disc-like morphology. The question is, why are we getting plate or disc-like precipitates instead of the spherical precipitates? The answer lies in something called interface coherency. When a precipitate forms in the matrix, there is an interface separating the matrix and the precipitate. And this interface can be coherent and coherent with strain, or semi-coherent or incoherent. Let's look at these one by one. For the coherent interface, that's when you have a perfect lattice registry between the precipitate and the matrix. This case is actually extremely rare. The classical textbook example is the aluminum-silver system. The GP zones in the system have coherent interface with the matrix. We will describe what GP zone is shortly. What is more common is coherent interface with strain, which happens a lot in the early stage aged specimens. In this case, you still have perfect lattice registry between the precipitates and the matrix, but due to the lattice mismatch, there's some strain stored at the interface, and the strain is elastic. In the schematic, you can see the red dots away from the center. They are more bent than being straight, illustrating interfacial strain. For both coherent and coherent with strain interfaces, they happen early on in the aging process. As you continue the aging process, these coherent interfaces will evolve into semi-coherent interfaces. As the interfacial strain develops, dislocations will be introduced at those interfaces to relax the strain energy, and those are called semi-coherent interfaces. As aging continues, the interface will eventually become incoherent. That is, there's no lattice matching between the precipitates and the matrix. In the precipitate formation, the rule of thumb is you start from coherent or coherent with strain interfaces, then it evolves to semi-coherent and eventually becomes incoherent. After understanding the coherency of interfaces, we can revisit why most precipitates, they are plate-like. For most precipitates, the nucleation happens on something we call the habit plane. The interface that lies on the habit plane separating the precipitate and the matrix is usually coherent or coherent with strain. Normal to the habit plane, these interfaces are generally incoherent. It's much easier to grow precipitates along these incoherent interfaces because they are at higher energy. In contrast, the migration of the coherent interface, which results in the thickening of the plates, they're much slower because you need to nucleate steps on those coherent interfaces to advance precipitates into matrix. Due to the much higher migration rate of the incoherent interfaces, the precipitates usually exhibit the plate or disc morphology. Next, let's look at a real-life example, which is also a classical textbook example, the aluminum-copper system. The first configuration is the supersaturated solid solution configuration. There's not much we can talk about here. If you do slight aging, you have GP zones forming. When we talked about the aluminum-silver system, we said the interfaces are coherent when you form the GP zones. So that's the same GP zone here, but in the aluminum-copper system. The full name for GP zone is Guinea-Preston zone. Guinea and Preston, these are two scientists, and this microstructural feature is named after them. For most GP zones, they are either one or two atomic layer in thickness, so they are very fine and very thin. Since they only have one or two atomic layers in thickness, they do not form a distinguished crystal structure. Many people refer GP zones as solid clusters as well. If you have a closer look at the aluminum atoms around the GP zone, you can see they are displaced from their original position, and this interface between GP zone and the matrix is coherent but strained interface. Increasing the aging time or aging temperature, GP zones will evolve into theta prime precipitates. Further aging leads to the formation of theta precipitates, and the theta phase, as you can see, the interfaces on both sides, they are incoherent. This is why it grows much faster laterally to form plate-like structure. Let's also look at the top two figures and see what we can learn from them. For the figure on the left, it shows the Gibbs free energy on the y-axis. The Gibbs free energy of the supersaturated solid solution is actually fairly low. As soon as you form GP zone, the Gibbs free energy goes up, which is actually unfavored. The evolution from GP zones to theta double prime, theta prime, and theta lowers the Gibbs free energy, which is also like a driving force why you have theta precipitates at the end. By the way, the microstructure of the theta double prime precipitates are not shown in the schematics below. Looking at the figure on the right, on the y-axis, that's temperature, what this tells you is at high temperature, it's much easier to form theta precipitates. At lower temperature, it's easier to form GP zones. Therefore, you can change the aging temperature to engineer different types of precipitates in aluminum-copper alloys. Okay, let's look at the effect of second phases or precipitates on the mechanical properties, in this case hardness of the system. The aging temperature is 150 degrees, so it's a fairly low temperature, and we expect to see predominant GP zones forming at the early stage of aging. The x-axis is aging time. As you increase the aging time, the hardness actually initially drops slightly. This is probably due to the recovery, and very quickly you can see an increase of hardness. And this is attributed to the formation of GP zones. And longer aging can lead to a decrease in hardness we call overaging. They are correlated or associated with the formation of theta double prime, theta prime, and theta precipitates. On the graph, you can also see the dislocation cutting mechanism and dislocation looping mechanism, which is also named as Orman mechanism. I will not discuss them in details here. For more information, you can refer to my dislocation precipitates interaction video in the dislocation series. One important thing I'd like to draw attention is that different aging temperatures can give you different hardness profiles. If you age at a high temperature, you get a curve more like that, shown by my cursor. And the initial hardening is caused by a combination of GP zones and theta double prime precipitates. We talked a lot on the precipitate growth, but little on the nucleation. Here we have one slide to quickly describe nucleation of precipitates. Like any nucleation events, heterogeneous nucleation is much easier than homogeneous nucleation. In crystalline materials, grain boundaries and dislocations, they offer the preferential nucleation sites for precipitates. In the example on the left, you can actually see bigger precipitates formed along the grain boundary. Because these precipitates are much larger, they removed the solid atoms around the grain boundary, forming the precipitate-free zone. The example on the right is an atom probe dataset from my PhD work when I was a student with Professor Simon Ringer and Professor Julie Carney at University of Sydney. You can see, again, dislocations, they decorate along dislocations. How do we know those are dislocations? Because there's also carbon segregation along those dislocations to form cultural atmosphere. In this video, we looked at the formation, growth, and nucleation of precipitates. One important thing we've got to mention at the beginning of the video is that any precipitation is a diffusional process. Solid atoms have to diffuse very long distances to form precipitates. And I think here is a good place to finish the videos on diffusional transformation. Starting from next video, we'll enter the last chapter of this video series, displacive transformation, which is also called martensitic transformation.